All right, so this is digging deeper with average atomic mass, part 1. So the first thing is when you are asked to determine the average atomic mass of an element, you just look to your periodic table. And your periodic table has 2 numbers for each element on it. It has a whole number, which corresponds to the number of protons, which is the atomic number. And then it also has a number with a decimal, which is the average atomic mass, not to be confused with the mass number, because the mass number is protons plus neutrons for a isotope. The average atomic mass is the weighted average of all of those isotopes. So when you're checking out a periodic table, the average atomic mass is this decimal number found down here. So on this very first question, it says, what is the average atomic mass of nitrogen? Easy enough. We just check the periodic table. We find that the average atomic mass of nitrogen is 14.0067. Different periodic tables round this number off slightly differently. This particular one goes out 4 decimal places. Don't stress if the periodic table that you're referencing only goes out 3 decimal places. It's perfectly A-okay. So the average atomic mass of nitrogen is 14.0067. And for now, we're going to call that atomic mass units. We do learn a new unit for average atomic mass later on. All right, so then we get to this next question. Express the following 2 isotopes of chlorine in nuclear symbol notation. Write them both as neutral atoms. Well, first off, this neutral atoms things tells me that I need my protons to equal my electrons. My positive charge must equal my negative charge. And then just a refresher, these numbers after the hyphen, those are the mass numbers. That's what's written after the hyphen in a hyphen notation. So first we find the symbol for chlorine, which is Cl. And then in the bottom left, I put my atomic number, or my number of protons, which is easy because that corresponds to the number on the periodic table. So the periodic table tells us how many protons. So chlorine has 17 protons. So on the bottom left, I put 17. That gives this atom its identity. It's what makes it chlorine. Then in the top left, I put the mass number, which is what comes after that hyphen. So 35 for this guy, 34 for this one. Now, if the protons and the electrons were not in balance, I would write something on the top right. However, this instruction said write them both as neutral atoms, meaning protons equals electrons. So in that top right corner, I'm just going to leave that blank. So those are the nuclear symbol notations for the isotope chlorine 35 and chlorine 34. Then we take a look at average atomic mass. Now remember, average atomic mass is a weighted average. You cannot just add them up and divide by the number. You have to do a weighted average. So this says we have element X, which is a fictitious element, and it has 2 isotopes. Isotope 1 has the mass of 62.93, and its percent abundance is 69.17%. Isotope 2 has the mass of 64.93. And a tip here, percentage has to add up to 100. So since we're only given 1 percentage, I know that isotope 2 must be the difference between 100 and this number, or 30.83%. So isotope 2 must be 30.83% because the percentages of all the isotopes have to sum to 100. The way you find the average atomic mass, pretty simple. We take, for isotope 1, we take its mass, which was 62.93. Then we're going to multiply by its relative or its fractional abundance, which is not exactly the same thing as percent abundance. It's percent abundance before you multiply by 100, which means we just need to move the decimal 2 places to the left. So instead of multiplying by 69.17, I'm going to multiply by 0.6917. So what this is going to tell me is how much of the mass of this particular element comes from isotope 1. Then I'm going to add that value to the same steps for isotope 2. The mass of isotope 2 was given to me to be 64.93. So 64.93 times the abundance of isotope 2, but again, not as percentage, as a fractional or what we call relative abundance, meaning I move my decimal 2 places to the left. And that's it. I just do this math, simplify, and that's going to tell me the average atomic mass. Now keep in mind, the average atomic mass has to fall somewhere between the masses of all of my isotopes, because it would be impossible for the average to fall outside of that range. So when you're working these out, that's a good kind of self-check you can do, because if you get a number outside of the span of your masses for your individual isotopes, then you know that you maybe miscalculated something. So I type all that into my calculator, and my calculator says 63.5466. I'm going to kind of pay attention to the fact that my masses only went out 2 decimal places, so I'm going to attempt to get this guy the same way. So 63.55 AMU. Another thing I want you to notice is 63.55 is closer to 62.93 than it is to 64.93. And the reason for that is because this particular isotope had a greater percentage. Just like your test grades contribute a greater percentage to your report card average, so your report card average is going to be closer to what your test grade says than it is to your daily grade. So now, what is the identity of element X from question 3? Well, now that I have an average atomic mass, I can check my periodic table and see which one of these has an average atomic mass closest to 63.55. And I find that copper is the one that has the average atomic mass closest to 63.55. So this element must be talking about element copper. Last one, this one's a little bit tricky because here we're looking for the percent abundance of each isotope, which means we're going to have to do some fancy algebra. The steps are the same, except instead of solving for the average atomic mass, in this case, I'm actually provided the average atomic mass, and I need to figure out what are the abundances of these two things. So I still take I still take the mass of the isotope, and remember, the mass number is what's given here behind the hyphen. So if you're not given an exact mass, it's going to be pretty darn close to whatever this number is behind the hyphen. So the mass of that first isotope is 14, but I don't know what the abundance is. And just like in algebra, when there's something you don't know, you call it X. So just like we did up here, take the mass, multiply by the abundance, except I don't know what that is. And then we're going to add it to the same thing for the second isotope. So the mass of the second isotope is 15, and we're going to multiply by the abundance. But I don't want to also call this one X because that would be assuming that this is 50-50. And I don't know if this is 50-50. What I do know is that my abundances, just like my percentages have to add up to 100. Well, when I move that decimal over 2 places, these abundances have to add up to 1. So if I call this guy X, and I know the rest of it has to add up to 1, I'm going to call this 1 minus X. Now be very careful, because the most common mistake we see when we're working these out is students putting X minus 1. This is 1 minus X because 1 minus X plus X adds up to 1, which is what this should add up to. Then we set it equal to our average atomic mass, which in this case we're told is 14.007. And honestly, they didn't have to give us this because they told us this was nitrogen, and I could have picked this number up off the periodic table. So from here, it's just algebra. I'm going to solve for x. So when I simplify a few terms, I get 14x plus 15, because it's 15 times 1, and then 15 times negative x. So minus 15x equals 14.007. I'm going to gather my like terms together. So when I add 14 and negative 15x, I end up with negative x. And then when I take this 15 over to the other side, 14.007 minus 15 gives me negative 1.007. Is that right? That doesn't feel right. That's not right. It's 0.93 something. Minus 15.993. I'm sorry about that. 0.993, but of course it is negative. Divide through by negative 1 so that I end up with x equals 0.993. Well, keep in mind this question specifically said what is the percent abundance of each isotope. Percentage, I just take this and multiply by 100 to get 99.3%. But that's only the percentage of one of the isotopes. Which isotope was that? Well, which one did we assign x? We assigned N14 to be x. So 99.3% of all nitrogen comes from N14. And then how much comes from N15? Well, the percentages have to add up to 100. So that means 0.7% must be due to N15.